Mm.
People, like in person, there's 2 people in the class, and I know the person from undergrad, and then there's 2 people online.
Really?
Yeah.
I think it'll be almost close.
Well, he said there's like 20 people.
Somebody must have not lined up.
I bet I'm on the wrong page. It was like, I walked in, and there were 2 people, like me and this other person, I'm like, hey.
Might be from us. That's what. Nice.
Yeah.
Yeah. It's pretty cool.
It's also a really weird 6 hours.
I think that's what happened.
So,
Hello again, everybody. Shall we start our review? What's that? Oh, the projector's not on, yeah. So we cannot start a review. That's okay. I think we can start now. So turn off the camera. This is recording. Share my screen. So we're going to have a quick review of the material we have covered in this first part of the course. The material for the exam is going to be the first 2 modules, namely the overall summary of the undergraduate process control with a twist, a bit more advanced topics. And then we had discrete time systems in a separate module. We had a little bit about frequency response in a separate module. And then we started a material which is going to be for the final identification and model building and all that. Okay. So the first topic we covered in the course was in the file introductory lectures, which is a quick overview of undergraduate process control, with emphasis on things that are important from a, so to speak, thermodynamic point of view, namely the same way the thermodynamics put some fundamental limitations about what is possible and what cannot be done. We wanted to have a similar idea about what is possible and what cannot be done with process control, things about being able to stabilize a system or control a system, do all of these things. So what control can do is what we covered in section 2 of this introductory lectures PDF. It can do a number of things. It can regulate. It can follow set points. It can optimize. It can stabilize things that are otherwise unstable. So it can do all of these things, and we can get all kinds of benefits, from safety to environmental compliance to profit maximization, or even feasibility of running a process. We know we covered in section 4 the idea of a block diagram, I'll repeat it one more time. You have a system which we draw like this as a continuous flow tank, which we have steering and a cooling jacket if it's an exothermic reactor, and there's coolant here that cools off the reactor. And all of this is metal. All of these elements here are real elements where you have an actual fluid flowing through and so forth. So you may have here variables such as the inlet flow rate, the inlet temperature, the volume of the liquid in the reactor, the inlet concentration of the reactant, the concentration in the reactor, temperature in the reactor. You may have the coolant flow rate, the temperature of the coolant, and so forth. All of these variables refer to actual fluids in this. By contrast, you may create a block diagram where every arrow is a signal. So you may have an inlet concentration and inlet flow rate and inlet temperature. And if you put a valve here, for example, so that you can manipulate that flow rate, the outlet concentration may be the outlet flow rate, sorry, may be an input, and you may have other inputs like the coolant flow rate, the coolant temperature, and so forth. All of these are input variables. The arrows here refer to signals. Okay, this is a block diagram, everything is a signal. In the same way, you may have outputs such as the volume in the vessel, the concentration of A in the vessel, the temperature in the vessel, and so forth. Inputs and outputs depend, of course, on the actual configuration, depending on whether you choose to indeed consider something as an input or whether you let it flow freely. For example, this variable f could be an input or it could be an output if you remove the valve and make this a free flow system where the outlet is whatever it is. It's important to keep this distinction. After a couple of times it becomes second nature, but it's important to keep things separate, not put a valve here because it makes no sense. Yeah, this is a signal, so there's no valve or anything. You cannot mix a signal with an actual physical equipment. It's not a very good representation of what you have. Section 5 of the notes, we talked about the 5 questions that one must address to design a control system. And that's because, I'll repeat that and we'll see it again in multivariable control. If you have a process, you have the process here at the bottom, and essentially for that process, you have lots of feedback loops where you take a measurement of a flow rate, you measure a flow rate, you pass that to a flow controller, and you manipulate a valve. It's a flow controller, and you manipulate a valve. So all of these are flow controllers. So think of those as PIDs, basically. But flow controllers need to know what flow rates to deliver, right? When they measure these flow rates, they need to know. So somebody has to tell them what these flow rates should be. So you have set point 1, flow rate set point 2, flow rate set point 3. So who is going to tell to these controllers what the flow rate should be? Example, we've done this several times. Take a simple distillation column, say binary. You may have the standard configuration, and you have here the reflux and the vapor, liquid and vapor flow rate. So these controllers here may be PID controllers. So those are flow controllers. They measure a flow rate and they deliver that flow rate. But to these controllers, somebody has to tell what the set point should be, right? So what should the set point be? Well, the set point essentially means what is the desire L that I want here? What is the desire V that I want here? That these days is done very frequently by a system which is called typically a model predictive control system. Sometimes it's called a SCADA system. That used to be an old nomenclature, which is not exactly model predictive control. It was a lot simpler, but nevertheless, SCADA is supervisory control and data acquisition. So it will be a little bit higher up than the PIDs, but it's not quite MPC. MPC is much more powerful because it does real-time optimization. And there's overlap, but people understand those things well in practice. So MPC would work here to tell what these flow rates should be. But the thing is, you don't produce flow rates. You produce product, you produce purities, for example. So you have the distillate purity here, or the bottom's purity of the liquid, and all these things. So who is going to secure these things? Well, here you may measure that distillate purity, send it to a controller again. The controller, sorry, let me do it from here actually. The purities. So you measure all of these. Now I'm putting all the arrows like that because this is a multivariable system. So you measure YD and XB and all these things. This thing does its magic and determines the actual flow rates that need to be delivered, but somebody has to tell to this system what is the actual set point. At what purity do you need to produce? If this is a deethanizer, what percent of ethane or the rest should you run this, or what should be this, the bottom purity? So for that, typically there is a real-time optimization system which sits at the top, which again takes data from the process. And I'm not going to go all the way now, but there is feedback here, and this system is connected to a planning and scheduling system. And those are separate, actually. And then above this, there is a business optimization system. And after that, there is also business optimization or just economics decisions such as, should I build a refinery or should I build a new unit or things like that. There is this cascade of operations with this feedback. You see feedback here, feedback here. There's feedback to this also, and there's feedback to this. And at each layer, you have a time scale which is very fast, more slow. Here it's seconds or split seconds, minutes, hours, weeks, months, years, and so forth. Okay. In this context, when you are down here at this level, that's where a lot of the engineering configuration takes place. It's this thing here. Where do I put these valves here? And what do I measure? Because here you see we're feeding back YD and XB, right? Well, should I measure this or should I measure something else? And here it's fairly obvious from understanding the process. But what if I have here a reactor and here a separator and I have recycling so that I can have a reaction separation tray and all that? What do I measure? What do I manipulate? So to make this systematic, we gave 5 questions. Question 1, question 2, 3, 4, 5. And it's what are my objectives, my goals for control? What do I measure? What do I measure and what do I manipulate? The control variables, the manipulated variables. How are these interconnected? And then eventually at the very bottom, I have the control law. Most of what we deal with in these courses is this, and there is maybe a little bit of that. This usually it doesn't receive very much attention, not because it's not important, but because it's covered in other courses. It is very, very important. If you screw up here, you cannot get things right down here. Okay. We emphasize this, and I emphasize this again in a review, because it's a very important thing. So section 6 in the notes explains that to do process control, you need a number of things. You need to understand the process. Okay, you need process. You need to understand measurements, a little bit about sensors and all that. You need to understand about manipulations, what things you can manipulate. So all this basically says control technology. So you need to know what is a DCS, what is a PLC, and all these acronyms, which we explain. At PLC, we explain. By the way, we said that there is tremendous overlap these days because all of these systems are digital. They are computers. So even though they're called different names, they are computers. And you can do anything you want in the computer. It's just that the interface may be different, the convenience may be different, the programming may be different. That's a computer. PLC is for programmable logic controller, things that your washing machine does. First it soaks clothes, then it washes for 15 minutes, then it rinses for 2, then it spins for 15, or until the sensor says your clothes are dry enough, and then you pick them up into the dryer or something. Well, this is programmed in a logic, and there is logic. In the old days, this would have to be done using the ladder logic, which is cumbersome. These days, you just write the code. And you can do plenty more. DCS is for distributed control systems. Distributed because in the very old days, you had a central computer in a central room to which all the measurements would go so you can do analysis. In fact, the computer might not be in your plant. The first controllers that were installed, there is a nice old movie which I lost track of, by the way. I'll find that movie again, it must be somewhere on the internet, about the El Segundo refinery in Los Angeles. They installed computer control, and all the calculations were done in a computer in a bank, because banks could afford expensive computers for all transactions, in San Francisco. So data would be transferred by telephone lines there. The results would be transferred back by telephone lines. There would be a printout, and the operator would key in set points to a system. This would be at this level, roughly. Okay? But that would be a central computer, so systems were centralized. When DCS came out, everything was decentralized. Why decentralized? Because now you could buy a PC, and you could buy a few of them, actually, and they're very cheap, and you could put them around the plant in various units. You have your local decentralized control system. Okay, so there's plenty of jargon on this. These are some important names that I mentioned here. And for control, as section 6 again says, you need to understand the process, you need to understand control tech, and at the end, last but not least, is you need to understand a bit of control theory. That change is probably the slowest. This is the one that's evolving the most slowly because theory is fundamental, so there has to be something really worthwhile to change it. If it's not worth it, you don't want to change it, because to implement a new theory into software is very, very, very expensive. Okay. With that, again, I'm saying that we spend most of our time dealing with this, again, fully understanding that all of that is important. And section 7 says, how do you design a controller? Well, to design a controller, and basically this means how do you design a control law? You can do it in a number of ways, but basically it can be trial and error. It can be Ziegler-Nichols, 1 or 2. And it can be IMC. This is good enough. You don't need much more. Trial and error and Ziegler-Nichols are basically for PID controllers. IMC is for PID, although it fundamentally allows you to create other structures, but chances are you're going to eventually apply it as a PID. You won't apply this in other structure. The tools, the control theory that you need to apply this and understand this and all that is a few things that are important to understand, although you do calculations by hand all the time, but it's more to understand how these calculations are done. And one fundamental element is Laplace transforms. Laplace transform is a dreaded topic, and one should perhaps abandon the name so that the fear factor can disappear. Because in essence, all that this does is help you do algebra rather than calculus with dynamic systems. Okay, instead of trying to solve differential equations and all that, you do algebra. Whether that's easier than whether doing algebra is with the transformation is easier than just doing everything in the time domain may be debatable. Nevertheless, it's not difficult. That's the thing. And it's not difficult because Laplace transforms, you need 4 facts. Fact 1, 2, 3, and 4. Okay. Fact 1 is ridiculously simple. The Laplace and its inverse are linear. Oh, what is the Laplace transform? Well, if you have a function of time or space or anything, you can create through Laplace, actually, let me do it this way, this or in the inverse, a function of S. We call it a function of S. S is a placeholder, basically, something we use to keep track of things. It's for the logistics. You don't do much else with that. So this transformation, L and U are linear. Nice. Laplace of linear combinations are linear combinations of Laplaces. Very simple, very powerful. Exceptionally simple. 2 is Laplace of exponential, which we deal with all the time. Actually, let's go the inverse. The inverse of this is e to the minus at. Well, for t greater than or equal to 0 and 0 otherwise. But we typically remove this and concentrate on this, which is the important part. And you might wonder, well, we don't deal with exponentials all the time. True. This formula is actually true when we have a to be real or complex. It's the same formula, except when a is complex, it's going to have a complex conjugate term in that Laplace transform, in which case the inverse is going to have something that has e to the minus real part of a plus j plus or minus j, the imaginary part of a. And at the end of the day, you're going to have times time. You're going to have e times minus the real part of a t, and then something here times the cosine or the sine of the imaginary part of a t plus something. I deliberately placed dots here because this is the same as the other yellow stuff I had here. For a real a, the real part of a is just a, okay? It's trivial. But now you have the imaginary part of a times t. So this is a trigonometric term. Trigonometric and exponential. Here you have just the exponential. We only need to understand those things mostly qualitatively. In terms of actual calculations, very rarely will we have to do everything from scratch by pencil and paper. It's only that you have to do it a couple of times to understand how it's done, like many other things. Okay. The third fact is for Laplace of a derivative. And the fourth is Laplace of a delayed function. Laplace of a derivative is related to Laplace of the function itself in a simple way. It's simple s times Laplace minus the initial condition, that's all. And Laplace of a delay is related to Laplace of the function without the delay through the simple exponential s. With these 4 basic facts, you can derive pretty much everything we cover. You don't have, notice that we haven't even defined what the Laplace transform is, how we calculate it. You won't, my claim is that you won't ever need it. Well, unless you go to graduate school and you want to develop some theory and you need to go far more deeply into that stuff, in which case you need a bit more. But for all practical purposes, to understand that stuff, this is all you need. You don't need more. Which takes me to 11, section 11, that says linearization of nonlinear ODE. So that stuff is great, especially when you deal with linear ODE. Why with linear ODE? Because then you can take Laplace, you take linearity, and boom, 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 you have the algebra working for you. Very simple example. Let's do it together. So first order system. First order system, say a heater. Okay, so you have the inlet temperature here. You have a coil that provides heat. There's steam. And there's an outlet here. So you say, how is the temperature at the outlet related to the temperature of the inlet? Well, you write a differential equation. You have dt over dt, something that has Ti plus the heat transfer, blah, blah, which is T at the coil minus T. And you have a bunch of terms, and it's all in the notes. And I'm deliberately using dot, 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 because the essence is not the specifics. You have seen this in many other courses. The emphasis is that here you have a differential equation. Can you make this linear? Well, what is this equation? First of all, this equation may not be linear, so you have to linearize it. But if it's linear, it's typically first order. You have a first order derivative. So typically, you'll write it as in the form T y prime of t. You have the first derivative plus y of t. This will come from this term is equal to k u of t. And if you have a higher order system, you may have a time delay. Okay. On this, you can apply Laplace transforms. So you'll get, if you apply Laplace, you get s times t times y minus y of 0 plus y of s is equal k u e minus e to the minus t ds u of s. And eventually you get the transfer function, so you get y of s is k e to the minus td s u of s tau s plus 1. You have the effective initial conditions also, which is tau s plus 1 y of 0. So this is your transfer function g of s. And this is the effective initial conditions, which for us, for a stable first order system, it is forgotten if the system is stable, which is why most of the time we don't pay much attention to this, because that's what we want to retain, how to influence by manipulating u, the output one. Okay? Now, if the system is not linear, as in this case, we can linearize it. The linearization basically says that what section 11 says. The linearization says if I have a differential equation y prime of t is equal to f of y of t and u of t, and this is the manipulated variable. Well, this is approximately equal to the value of this at steady state, which by definition is equal to 0, plus the partial of f with respect to x at steady state, y of t minus ys, plus the partial of f with respect to u s u of t minus u of s. So this is Taylor series, right? And you can show rigorously that if the linearized system, which is now, let's write it a little more cleanly, this is delta y of t, this is delta u of t, this is, you can call this b, you can call b lowercase, you can call this a, this says y prime, delta y prime of t is a delta y of t plus b delta u of t. Okay? And this is in the sense approximately equal. There is rigorous theory that says this is not just for convenience and then hand waving. This is rigorous in the following sense. If the system has this steady state that I just identified, by the way, steady state means 0 is equal to f of y at steady state, u at steady state, right? By definition of a steady state. This is by definition. That's how the steady state is defined. Steady state definition. If I have a steady state, ys, us, and I do this approximate linearization through Taylor series around the steady state, and I find that this system is stable, the linearized system, which means a is less than 0. So this equivalent linear system is stable. If the linearized system is stable, then there is a neighborhood around that steady state for which the nonlinear system is stable. And of course, the caveat here is, okay, there is a small enough neighborhood around which the system is stable. And how small? Well, that's much, much harder to get. However, in practice, you can get that through some simulation. People do this all the time. And it works extremely well for most systems. You can find how far you can go. There is also theory that can actually help you tell how far you can go and what are the initial conditions or the inputs to the system. Oh, that take you far enough to check whether you've gone too far. By the way, I also mentioned the term a neighborhood of the steady state. What does that mean? It means initial conditions away from 0 and values of u away from 0 as well. Okay? So there are values of initial conditions plus or minus 0, plus or minus something away from 0, and values of the input u plus or minus away from 0, such that the system remains stable. Theory guarantees that. Just doesn't tell you how much that is. But you can find that with simulation, like I said, fairly well. So it's practical. This method, this approach is very practical, which is why people use it all the time. Most, if not all, controller design for chemical plants at that level is done with linear systems. The only thing that people may linearize, but that's an easy one, is this delta U. You may have a valve there and you want to say, how does the valve opening affect flow rate? Well, you've seen valves and flow rates, right? This is the percent valve opening, 0 to 100%. And this is flow rate. So you may have a perfectly linear valve. There aren't very many of these. You may have valves like this. 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 Okay, you've seen those things in practice. The manufacturer will tell you what kind of valve you have. If you have a Fisher valve, it will tell you what it is, if it's a control valve in particular. And then what you do is you take that function, put the inverse there of that function here in delta U so that you can have essentially a linear effect from whatever it is you assume to be manipulated to the output. Right? So that's a trivial part of removing a nonlinearity. The dynamic part, which is more interesting, is typically handled like this. That's what people routinely use overwhelmingly, almost always, assuming a linear system. Incidentally, where they do deal with nonlinearities seriously is here at the RTO level, real-time optimization. But here the optimization is done assuming steady state systems, because this is over the next 8 hours or 12 hours, my shift. Where should the plant be running? So you say, what is the optimal steady state? For that, you need a serious nonlinear system. You need an Aspen or HYSYS model or something like that. And people do this, but it's difficult. So there is an ongoing debate. Is it worth it? Some people are abandoning, some people are intensifying efforts. This is a developing technology as we speak. Okay. Back to our main review. So this is the idea of how we analyze systems. We use linear theory. And chapter 12 again says, what is controller design? Well, we mean the control law. 17 talks about controller design in a multi-level structure, which is exactly what we mentioned here. This is section 13 of the PDF notes. And then section 14 says, what is controller tuning? Controller tuning basically says, I have decided what is my controller structure. It is something like this. And then I want values of the parameters, my controller. That's tuning. Tuning for a PID, for example, means if it's a PI, means what is the controller gain? What is the integral time? Kc and tau y. That's controller tuning. For PID in particular, I showed you these two papers lumped into one that have about a couple of hundred tuning rules for PIDs. Okay, those are not needed. There are minor differences between them, and just a couple of that, just that stuff is going to be good enough for you to do the job. Section 15 summarizes one more time how a controller is designed. It explains that you need a couple of things. You need something for controller design. For controller design. You need something about the process. And then you use that information to design the controller. Usually, the knowledge about the process is I know how my MVs affect my CVs. Okay? But not always. It could be in the form of a process plus a P controller. If I build a feedback path around them, this behaves in a known way, in a certain way. Particularly, this is the ultimate gain. That's what the Ziegler-Nichols tuning rule, the second tuning rule, relies on. But most of the time, this is how knowledge about the process is encapsulated. In a model, a dynamic model that says if I change my MV, it's going to change my CV in this one. Perhaps the most important part of that is the steady state gain. You need that. And then you also need, if there is dead time, you need to know the dead time. And eventually you need to know a few things about the time constant, the dominant time constant. So section 16 talks about what we said are the three basic approaches to tuning or designing and tuning a controller, and there are various criteria. Before we do anything, we need to specify what is our goal? What are we trying to do with controller tuning? Well, there is a number of objectives. For example, you need to have good set point response. This is good servo. So you change the set point of your closed loop. This is my closed loop process, controller, maybe disturbances, go around. This is my set point. This is an entire closed loop. The input to this loop are disturbances and set points. The outputs of this loop are the output of the process, but also the input to the process. It's an important distinction that sometimes goes unnoticed. This is, let me use another. This is an input, and so is this. So green are the inputs, yellow are the outputs. So in essence, what I'm saying is that if I wanted a block diagram, these are my external inputs, and these are my two outputs. U is now an output of the whole system. The controller does it. You don't manipulate it separately. It's the controller that does its thing. So you have to tell how your closed loop behaves by looking both at Y and U, and not just Y. It's very, very important. So what kind of response do you want? Well, if you change the set point like this, Let me use green then here to suggest that you make this step change to the input. You make this change to y set point. You want the output to respond in a nice, clean way. So you would say this is better than this, which takes forever, but it may be worse than this. And how do you assess this? Well, you can assess it by looking at things such as the squared error or the absolute error like this. So if this is my response, the error here is this, right? This plus that. If you just sum up the areas, this is just the absolute error. If you take the square of these and you sum them up, it's the squared error and so forth. Sometimes people say, I want to look at the rise time, so I want to make when this is reached the smallest possible. Sometimes people say, I want this to be the least possible, the small. There are many criteria. Controller design is a business where setting the criteria is not immediately obvious and trivial. Sometimes people say, I want a response that is in this envelope. Something. So this would be nice, it would be in this envelope, but if the envelope was like this, people would say, well, here you're violating the envelope. That's not a good controller. Go back to the drawing board and redesign your controller. So specifying these control goals is important. Other control goals, well, when you have a disturbance. So you have a disturbance. What kind of disturbance? It could be anything. It could be a load. It could be a heat exchanger or a heater. A heater where all of a sudden you switched the feed from from feed A to feed B. Feed B happened to be sitting outside at a lower temperature, so all of a sudden your heater has to deal with a fluid that comes in at a lower temperature or a higher temperature, just to do it like this. So or lower. It was sitting outside, it comes at a lower temperature. Okay, so you have a disturbance. Well, you want the output, which is the temperature of the liquid coming out of the heater, to jump the output Y. It would go like this, and you want it to go back to the value you wanted, right? So this is good, this is better. Perhaps this is not as good. There's oscillation. Perhaps this is good. And you see now that I have trade-offs. So how do I trade-offs in the sense you may have oscillations, but as long as the oscillations don't last too long and the peaks are not too high, I'm okay. How do I quantify these things? Same story. I can take the squared error, so the integral squared error, or I can take the integral absolute error. What are these? So integral 0 to infinity of the output y of t dt absolute. I want the area under y of t, the absolute value of that, to be as small as possible. So I try to minimize by selecting my PID parameters. For example, I'm picking kc and tau y. I may have to solve this optimization problem. And because that depends on it must be for a certain disturbance. Or you may do this as a ratio because it's a linear system. Okay? All of this can be done. And there is enormous, vast literature that solves these problems. People have solved these countless times. And there is no point in going over all that algebra because if you ever need it, you'll know how to do it or where to find it. You look up the literature, you'll find it. The integral squared error is a similar thing. You have this, but now it's y of t squared. The set point is at 0, right? This is at the 0 level. This is y of t versus t. So you may do the integral square here by minimizing with respect to kc and tau sub I. this expression here, which is the integral squared error. This is squared here. This is absolute. All these things are done in textbooks for undergraduates. Even Stephanopoulos has that, Seaborg has that. Many other textbooks discuss these things. It's a classic topic. The thing is, most of the time, you don't do a rigorous optimization numerically. You just do trial and error and say, my design method suggests this. Let me change those. Is this okay? Good, I'm done. And that's how this works. Now, these are goals. These are the objectives that I have for my controller. How do I achieve these? Well, one, I already mentioned, one way I achieve these, it's trial and error. If I have my PID, I have KC and tau I can do lots and lots and lots of simulations these days. I can look at the results, done. One thing that one needs to be careful, of course, is that when one does these simulations, it shouldn't be only for nominal performance. What does nominal performance mean? Well, I have a model for my system, right, that I'm trying to control. For that model that I have, I designed a controller. The controller works well. How do I know this? I did several simulations in the closed loop, and the closed loop behaved well. However, the system that I'm using in my simulations is a model. It's not the real system. So the real system may be a little bit off. In fact, it will be off one way or another. Why one way or another? Even if my model is super accurate now, down the road, there will be some drifting in my process, I'm pretty sure. So the model is not going to be 100% accurate. It will drift a little bit, maybe a lot. Maybe it will drift a lot. Not to mention that I may even change my steady state operating point. This is done all the time in plants, especially large plants for profit, in which case the model will be off. Is my controller robust? So what does robust mean? It means I designed my controller and it works well for the nominal model. Is my controller going to work well for a perturbed model and a reasonably perturbed model? I need to consider this in my simulations. How would I consider that? We did some examples. We modified some parameters in our model and checked how the control system behaved. Okay, so with that, I can assess robustness. Actually, there is plenty of theory on how to design the controller for robustness. And we have given some ideas of that based on tuning rules, which I'm going to come to right now. The Ziegler-Nichols method is great, not so much because it gives you a super duper controller nominally, but it gives you a robust controller. It handles the robustness case. Ziegler-Nichols knew that your model is going to be off pretty soon, if not from time zero. Same thing for IMC. IMC says, yeah, I can design a perfect controller. I can make the response perfect and all that. The real system is going to have some dead time that it didn't account for. It's going to have different gain, different time constant. Before I know it, the system is going to, the closed loop is going to be so bad if I overdo it with my controller aggressiveness that my closed loop may even become unstable. Let's say those things, how these things work now. So trial and error works quite well, but you need to be careful to do for robust nominal performance and for robust performance. In fact, people sometimes distinguish these things. It's a matter of jargon. They say, I want definitely robust stability and robust performance. Well, why do people distinguish this? Because if you don't even have stability, well, good luck. Okay, it's a system that is worthless. So the bare minimum that you need to ensure for a controller is robust stability. It's the bare minimum. The system you design, the controller and the process and the closed loop, namely the whole system you just designed, must be robustly stable. Again, robustly means if the real system is slightly off from what you assumed in the model, the system still works well. It can be controlled well. That's a robustly stable system. And robust performance, well, it means that the performance is still good. Namely, disturbances are rejected within reasonable time, or set point changes are tracked within a reasonable time. Okay, and we discussed those things. There is discussion in the notes. There are several examples where there's the orange blocks and the blue blocks, the slightly perturbed blocks. And the simulation show you how the performance changes in an acceptable way or in an unacceptable way, so that you can visualize these things. This is trial and error section 16.2, and there is some rudimentary theory, of course, that guarantees the properties we want, and it also guides you as to in what way you need to do the trial and error. For example, if the process, sometimes people use the term open loop, namely the process itself, or sometimes it's the process in the controller. Let's just say the process. So if the process is stable, then we know that robustness of the closed loop is equivalent to lowering the controller gain. If you increase the controller gain, you make the controller more aggressive, you jeopardize closed loop stability, and your loop is not going to be robust. Theory explains those things. Well, let's just give the final outcome of this theory. Of course, if your process is unstable, things are different. Then you need to have a higher gain so you can intervene strongly enough to stabilize your process. You need to move in the opposite direction. If you don't intervene strongly enough, you cannot stabilize your process. It's the reverse. But we emphasize mostly stable processes to instill some sanity. For now, we'll go to unstable processes in the coming lectures. That's trial and error, 16.2. 16.3 is Ziegler-Nichols. Ziegler-Nichols comes in two varieties. Namely, you have the reaction curve, make a step change on U, look at the response. From these two, get your transfer function. And then from this, you have your beautiful table that says gain, integral time, and derivative time for P, Pi, and PID must follow these formulas, boom, 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 boom. And there are formulas. Those are not meant to be the ultimate, always usable numbers. In fact, even Ziegler-Nichols in their original paper in 1942, those have been around since 1942, and they're very good. There have been countless improvements, but I would say this is worth understanding. And in that paper, they tell you how you modify this. They tell you if you don't get what you want, well, change things in that way. You get too many oscillations, well, lower the gain a little bit, perhaps. It takes you too long to reach a steady state, well, make the integral term more aggressive, reduce the integral time. I mean, they knew those things. Ziegler-Nichols knew those things very, very well. But they give you this table because it's so useful to just have one table as a very simple starting point that works most of the time. And you also know how to move things around so you can get what you need. This is a Ziegler-Nichols version 1, and then there is version 2, where the thing about the process is not in the form of this. The thing about the process is in terms of the ultimate gain. So you have disturbances and set points, and the idea is that if you change the gain of this controller, if it's small enough, you see, look at the output, and it keeps going. It's just the disturbances, right? You increase the gain, so in this direction, so when you move down like this, the gain goes up. So this is going to start moving more. And at a certain point, the output will go like this. I'm not drawing this as a smooth curve. Actually, it's easier to present this as a smooth curve. It's going to be a nice periodic curve because it's easy to visualize it. In reality, you don't need that. And you can even simulate it like this and have it in the notes also, or in old exams and in homework, so that you can see that this can be a noisy curve. It doesn't matter. Take your pencil and do that, or if you want to be sophisticated, filter it. It's easy to filter this, or smooth it, because you have the whole signal. So this happens, what is this? The continuous oscillation happens at the ultimate gain. There is a value of the gain here for which you have continuous oscillations. So you can measure the period of these oscillations, the ultimate period, and then boom, you have again a table in the same way as before. You have Kc, tau I, tau d for P, Pi, and PID. And there, boom, 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 boom. There are formulas here that tell you how you can go from the ultimate gain in the ultimate period to values of Kc, tau I, and tau d. Works well. Ziegler and Nichols tell you actually that this gives you 1/4 decay ratio of the closed loop. So if you have the closed loop and this is y set point, and you look at the output, of course, there is an input here and there are disturbances. But if this is a step, the output will behave like this. And this here, which is the decay ratio, is 1/4. What's magic about 1/4? It's clean, small enough, fast enough response. They could have made it smaller, but then you might have to wait longer and you might have other issues. It's also robust. In fact, Ziegler and Nichols calculated both for this and for that the gain in the phase margin, remember we said it is when you have the logarithm of the amplitude ratio and the phase, and you plot for these, you plot not for, you do the whole closed loop. When you have the closed loop, G, C. Theory says in Bode plots that if you do a Bode plot for this G times C, you can draw conclusions about stability of the closed loop. How? Well, this is your amplitude ratio, the gain curve. You have the phase, which is something like this. You go to minus 180 degrees. So this is minus 180. You go up here and you go here. Is this point above 1 or below? If it's below, you say, nice, I'm stable. Well, when you do this, for the Ziegler and Nichols tuning rule, we have here a margin which is about 50% of the nominal gain. In other words, the gain could double and you would still have stability. And the phase margin, if you go in the reverse, if you go here and you say this is the critical value, so if I go down here and here, am I above minus 180 degrees? That would be here. This point is the 1 here in the obliteration. This is the phase margin. That is about 60 degrees for Ziegler and Nichols. And so there was beautiful theory and nicely theoretically analyzed by Ziegler and Nichols. And it's interesting to understand these things, but we want quickly because we don't want to turn this into a math course. Okay? But it's useful to know qualitatively what Ziegler and Nichols buys you. It's not just, well, here's a table, do use it, done. Here's a table, use it, and understand that you may have to modify how, using the theory he said, for example, for faster closed loop response, increase the gain, to improve robustness, decrease the gain, things like that. And how far are you from destabilizing a closed loop? Well, you're this far, 60 degrees in the phase, 50% of the nominal of the critical gain for the gain. All of these things. This is Ziegler-Nichols. Finally, we have IMC for controller design. And we said for IMC, the idea is you have a loop controller process. All disturbances lumped into one. Let's make it G. Doesn't matter. So this is your closed loop. So minus here. This is equivalent to a closed loop that has everything the same except G. This is the disturbance. Everything is the same except now your controller has a structure which has Q here. It has a model of the process, which you assume be perfect, and you subtract this from the measurement from here. And what you feed back is that error. It's the difference between the model output and the measurement, Y. And it turns out that if you write Y as a function of, to find the effect of set point and disturbances and maybe noise, and include that if you want. So this is the same for everything in the denominator. And the numerator has GC minus GC1. And if you take this, this is Q. If you write this as 1 minus GC1 plus GC, now this is again Q. And of course, this is Q. So that says basically what this picture shows, and you can derive this again from the algebra. So this is GQY set point plus 1 minus GQD minus GQ. And so Q, Q, Q. The beauty of this is with, I forgot to say, well, I said it, but I forgot to write it. G tilde is assumed to be equal to G for all of that. That's why there's not G tilde anywhere. The beauty of this is that from this simple idea, rather than trying to guarantee stability by finding the poles of the closed loop and ensuring that the poles are in the left plane and all that, it's trivial now because closed loop the closed loop is stable if and only if Q is stable. And that can be proven in half a line. It's the half a line proof. So why is it that if Q is stable, the closed loop is stable? Well, G is stable, as we said already several times. Let me emphasize it one more time. It's for stable plants. So this is stable times stable, stable. One is stable plus stable, 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 trivial. You just multiply stable things. If Q is stable, the closed loop is stable. And it's necessary. If the closed loop is stable, Q must be stable. Why is that? It's because, remember, the closed loop does not have one output only. It has two outputs, Y and U, and there are Y set point and disturbance. And U has the same structure. Y set point plus this times this plus this, and the denominator is the same. And then Y set point to U is C, and disturbance to U goes minus C, so minus C, and noise to U is minus C. Okay, so this is Q, this is minus Q, this is minus Q. Okay, so if the closed loop is stable, all the transfer functions from external signals, from these external signals to the internal signals in the loop, the internal signals generated, must be stable. Therefore, this Q must be stable. Okay? So that's how we prove the necessary and sufficient. It's the half a line proof. Extremely simple. So Q stable is necessary and sufficient for closed loop stability. If Q is stable, the closed loop is stable. And if the closed loop is stable, Q must be stable. Which means now controller design is simple. I just need to pick a nice, simple, stable Q. I know how to design stable transfer functions. All I need to worry about is poles are in the left half plane. In fact, this gives me more because it says this must be about 1, this must be about 0, and this must be about 0. And I've said several times that these two are nicely compatible. Nice. This with that is not nicely compatible, but what saves the day is frequency response. You can choose GQ to be almost 1 for low frequencies, almost 0 for high frequencies, where noise has most of its power, right? Or a lot of power, let's say. Which means if GQ must be approximately 1, that means Q must be approximately 1 over G, which means let's try Q equal to 1 over G times F. Of course, Q must be stable, so this must be stable. If it is stable, good, everything is okay. If 1 over G is unstable, well, then make Q to be, well, if it's unstable, it says it has things that are in the numerator, and the denominator has S plus A, right? Or let me minus A, doesn't matter, A is a number. And the pole is in the right half plane. Okay. Well, use then for Q, 1 over G, same things as here, this is 1 over G. So use 1 over G, everything the same, except now put a minus sign here. And then use the filter F. And filter F is typically 1 over lambda S plus 1. In fact, frequently we make this to power R so that the degree of the denominator in Q can be greater than or equal to the degree of the numerator. That's simple. And of course, it also has to be what we call causal, which means if 1 over G is not causal, 1 over G has stuff that says e to the plus theta s, which is not causal, then this is one part and this is the non-causal part. We just remove it. And we just say Q is the dot, 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 dot. Make this equal to 1 and multiply by F. Done. There is an element, a sense of optimality for these choices, not just simple playing with symbols there, drawing nice lines and all that. There's a sense of an element of minimizing squared errors and all these things. Let's keep it simple. These are the rules. So this is IMC. That's the full IMC. For first order model, for first order, IMC is PI. For second order, IMC is PID. For first order plus time delay, first order plus time delay model. So this is for the model. IMC is Smith predictor. And in fact, for all of these, actually those are already PID, but for any model, we can have IMC to be approximately like PID. And in fact, we can have the same thing that we did for P, PI, PID, Kc, tau y, tau d. We have the corresponding formulas for your IMC. The only thing is that the nice thing about that is you have only one tuning parameter, lambda. It's just the lambda parameter. Lambda is what appears here in this filter. It's the time constant of the closed loop. And there is a guideline actually, because we typically use first order plus time delay as our model, then if we know this theta, theta is equal to theta nominal plus or minus delta theta, right? Well, use lambda to be greater than delta theta. Make it 2 times as large, something like that. Definitely don't make it smaller, because if you make it smaller, there is a chance you may destabilize your closed loop. Lambda, if lambda is greater than this system is robust. Robust stability and robust stability and robust performance. If you make lambda less than delta theta, you will likely run into robust stability problems. Okay, so that's how you see. Now, all that can be done, not all that, some of that, for example, the second Ziegler-Nichols method that we mentioned, this method, can be done automatically these days with the self-tuning regulator STR or self-tuning integrated controller. There are various commercial products in the markets. The self-tuning regulator essentially, instead of doing manually changing the gain to create a continuous oscillation by making the input an oscillating input, it has the following trick. It has here an on-off switch that says, if the error is positive, you do like this. If the error is negative, you do like this. Okay? So this is the input U. It goes to the process, and the process, you may assume something like this. So the slightest disturbance here or set point change here will bring the closed loop into a continuous oscillation in the input, because the error would be positive, negative, positive, negative, positive, negative, in which case U is going to be up, down, up, down, up, down, up, down, which means that the output will be to continuous oscillation, from which there are formulas, I have them in the notes, that allow you to find KCU. So you can find the ultimate gain and the ultimate period. And then you use this. And it's done automatically. Controllers have a button if you want to do it. You cannot try this on a distillation column, because to bring this distillation column to continuous oscillation will probably take days. Okay. Columns are very slow, so to bring it to an oscillation is a good luck. But you can do it quickly on PUM or an exchanger, something quick that has a short time constant. So section 18, that was in section 17. 18 talks about capabilities and limitations of feedback control. That's a nice qualitative discussion section that explains that feedback can regulate, feedback can stabilize unstable processes, feedback can destabilize stable processes if not done correctly. Feedback tolerates uncertainty to some degree, not any uncertainty, either in the model or in the disturbances. So these are basic capabilities. The basic reason why feedback works is that it's robust. It can tolerate uncertainties in the model and in the disturbance. Doesn't need to know them. But it needs to know something about the process, not just any process. A critical element about the process is the sign of the steady state gain. If you make a step change in the manipulated input, the output eventually goes here. In fact, difficult processes are processes with inverse response, not this, but this inverse response. Because you think maybe the process would go like this, but eventually it goes up. Well, if it does it, if it goes up, the steady state gain is positive. You need to know that. If you get this wrong and you think it's negative instead of positive, you cannot stabilize, you cannot design a controller, basically. You may easily get you'll get instabilities in the closed loop if you have a controller with integral action at PID. Frequency response to section 19. In fact, we had even a separate section on this. We discussed about frequency response. We said, why frequency response? Because if you have a process and any input and an output, well, the input can be expressed in a sum of sines and cosines. So sines, more frequencies. So all of these can go to the process, and each one produces outputs. And whether you take each one here and look at its output, this, and look at its output, this, and look at this output, or sum them up first, here and here, throw it, and look at the output, is the same because the process is linear. It's linearity that allows us to do this, which means I can look at a single sine. So I have my process, I look at a single sine, a sine omega t, that produces an output that is eventually another sine, a hat sine omega t plus theta. The frequency is going to be the same. However, A, the amplitude, is going to be different from A hat, which is why we have the amplitude ratio. So A hat over A is the amplitude ratio. And when we have a phase, namely there may be a delay, or it may be actually a predictive, a positive phase. So this is the phase. Theta, and you can get these, the amplitude ratio is the G of J omega in terms of the transfer function, and this is the phase of G of J omega. And you can plot these, you can even use these to understand controller design. If you have the amplitude ratio and the phase, we explain that you take where the amplitude ratio is 1, you go down, you look at the phase here, and if it's above minus 180, oh, this is a plot for G times C. This is called the open loop system. It's G times C. You don't have the feedback back. It's not 1 over 1 plus GC or anything. Just G times C, that's all. If this point is above minus 180, that means the closed loop will be stable. Nice. And it tells you how far you are from instability. So you have a notion of robustness. But more important is the filtering properties that one can understand from frequency response. That says these frequencies to the right are filtered out. These frequencies to the left essentially go through. From these frequency ideas, we can understand how noise and set points, even though they correspond essentially to the same amplitude ratio, in fact, exactly the same amplitude ratio, set point has frequencies in this range, noise has many frequencies here. You can filter out this closed loop noise. You can keep the set point changes and follow them. So this was the first part, which was a quick review of undergraduate process control. There was also a discussion about discrete time systems. For discrete time systems, essentially the section that I have at the very end of the notes, let me find the corresponding page really quickly, that has these. So discrete time systems. In discrete time systems, we have a table at the very end, which is on page 23, that tells you what are the tools that one uses and how there are counterparts of these tools and continues. Okay? I don't want to turn this course into an exercise in algebra, but the concepts are simple and the calculations are not difficult either. Okay, the Z transforms has three facts, 1, 2, 3. The first is about linearity, linear for Z and for Z inverse. The second is the Z inverse of 1 over 1 minus PZ inverse is equal to P to the K. And finally, Z of a shifted function, Fk plus something, K0 is actually plus 1. It's Z times Z Fk plus a term that has to do with the initial condition. But the main thing is you have plus 1 and you have Z to the plus 1. It's as simple as that. The rest is covered in the table on page 23, as I said. And the idea is that if we have a closed loop, one has to remember, as we have the closed loop, we have a continuous signal here, Y. Then there is a analog to digital converter, which creates here a discrete version of this signal. At each point, takes a sequence, creates a sequence YK at each point K. This goes to the controller, processing the controller. The controller generates a sequence, and then you have a digital to analog converter that creates an analog signal U to the process from the controller output. Okay. How this is understood by the controller to generate that is where the Z transforms are useful. Again, I would like to keep this to a minimum and not turn this into a course in algebra. And incidentally, how we go in the other direction, how from this we get this, or how from this sequence we get that sequence. Now going in that direction, we said if we have differential equations, essentially for every derivative at time tk, we say this is approximately equal to a finite difference. You put it there, and from a differential equation, you get a difference equation. Difference equations are just for sequences, not functions of continuous time. We did some examples also, and there's plenty of algebra and lots of programming. And like I said several times, computers love the IJKL indices and all that. They are the element. We humans prefer images and expressions and all that. We understand things much, much better. Combining the tools that computers provide, we can do a good job in understanding those things. That's basically what we covered. Okay, and we have two homework problem sets, so you can make sure that you don't miss the bare minimum of knowledge that would be needed for something like this. There are also old exams that cover those. Nice problems that you can try to solve. Most of these problems are from the real world, by the way, or projects that I did here and there, or papers we wrote, or consulting jobs, or industrial projects through the university and so forth. So I'll stop here. I don't know if you have any questions at this point.
Yeah, shall I ask a question?
Say it again.
Can I ask a question?
Yes, absolutely. Go ahead, please.
In discrete, there is a question, example number 5, in that you took the transfer function 0.5 z raised to -1 divided by 1 minus 0.5 multiplied by z raised to -1. What is the logic taking that? Because we have the function with 0.50 raised to minus 1 divided by 1 minus 0 raised to minus 1 multiplied by 1 minus 0.5 raised to minus 1.
Okay.
So
Me-
how did you come up with that?
It's a little difficult to follow. Let me, what you're discussing. So first of all, let me,
Can,
give me just one second.
can-
I'll let you share your screen. If you want to write down something, I'll show something. So security. Do you want to share your screen? I'll stop sharing.
yeah, I can.
Yeah, so that you can show me what you're referring to. It's going to be a lot easier.
Yeah. So this uh, example number 5.
Yeah, I'm not seeing your screen yet.
Oh, really? Some reason. Window. Okay. Can you see now?
Ah, excellent. Okay, very good.
Okay. So
Okay.
this particular question, f of z with the c, transform,
Mhm.
you came up with the transfer function that is 0.50 raised to minus 1 divided by 1 minus 0.50 raised to minus 1.
Yes.
So how did you come up with that transfer function? Because you have 1 divided by 1 minus 0 raised to minus 1.
Yes.
So how do you come up with the transfer function?
This is not a transfer function. This is just a z transform. Actually,
Yes, z transfer function.
yeah, the
sorry.
z transform. If you look at this, hold on, let me see. I think I can annotate. Give me just one second. Where is the never mind. So the idea is that if you want to think in terms of transfer functions, the 0.5z, the numerator over the second part of the denominator can be thought of as a first order system. And the 1 over 1 minus z to the minus 1 can be thought of as the z transform of a step. So if you want to think of this as transfer function times an input, the input is a step, the transfer function is first order. But this is just a z transfer function. Now, to do the inversion, you need to use one of the 3 facts that we have learned about z transforms. And the second fact says just make everything a sum of first order fractions. So the 2 fractions, let me see if I can, let me do it differently now. Hold on.
Yeah, I can
I'll
stop sharing if you want.
continue, yeah. So what I'll do is I'll open that file so I can write. Just one second. So, Dropbox. And that was example 5, right?
Yes, there's example 5.
Okay, good. So the thing here is, annotate, so let me see if I can write, good. So as I said, this can be a first order system. 1 over the denominator can be thought of as a step. So essentially you have a first order system that experiences a step, and there's something here that is the output. So it goes like that. Now, remember the three basic facts, right? The second basic fact says that this is the kind of Z transform which we can invert easily. So whatever fraction we have, we need to bring it into the form of rational fraction sum. You need to bring it into this form. And if it's in the form of Z polynomials, change that to Z inverse polynomials, write it again, like I said, in the form of numerator over denominator, and eventually do partial fraction expansion. So this is the partial fraction expansion here. Once you have that, then each one of these is trivial, right? It's just a
I found that 1 by 1 minus 0 raised to minus 1 is a step function in Simulink. So we can test it, and if if it is
it will give you exactly that. It will give you-
behave the okay, good, thank you.
Or if you remember, I've given you some homework where I have given you specific commands which you can use in MATLAB and in Mathematica, so you can get the inverse of this, right? Give it this transfer function, and it will give you this output, which we derived manually, so we can understand how this works roughly. Is it any more clear now?
Yeah, fine, thank you.
Very good, very good. Other questions?
I had one.
Yeah, go ahead, please.
Hey, for one of the exams that we were looking at, I think it may have been 2022, for an integrating process, like a transfer function, I think it was like 1 over SA.
Okay, let me do this then. Let me close, let me stop sharing for a moment. Let me go to, it was 2022, you said?
Yeah, I think it was 2022.
Okay. Oh, I can get it. Let me get it from Canvas.
And while you're getting that, I'll just speak. I was just confused about what is the proper way to go about tuning a controller for an integrating process like that. Because if you do an open loop,
yeah,
it's just go to infinity.
For an integrating process, the easiest way is probably by trial and error. Although even the Ziegler-Nichols paper had some ideas, and there are techniques to do that. But trial and error is good enough there. Give me just 1 second to find this.
That's kind of the impression I got from the answer key, at least, but I wanted to hear it from you.
And you may have seen that you can abuse a little bit theory and use IMC as well, because it's fairly straightforward. But give me just 1 second. I'm just logging to Canvas, and I need to go through a dozen screens to make sure I'm not hacking the system. Okay, so I'm there. Okay, so now I can share my screen, share screen. So it was all the exams 2022, right?
I think so.
So exam, this one, right?
Yes.
The PDF. So was it this one?
Yeah, so you're tuning the controller for tank 1, and your transfer function is really simple. I mean, it's just 1 over S times A, which is it's as an integrating transfer function, right? So if you try to use Ziegler-Nichols in open loop, it's just going to go to infinity because you just increase the flow rate without.
Yeah.
So I was just asking, what is the appropriate way to tune something like this?
Yeah, you can. Well, there is trial and error, but let's see.
It was the very final problem that talks about.
Yeah, if we do here, if we go here, you see this, that it's 1 over AS. So this is on the verge of instability, right? So it won't blow up. So is an integrating process stable or unstable? So strictly speaking, it's unstable in the sense it doesn't go back. If you throw in an input, the input will be integrated, so the output is not going to come back to to 0, right?
Mhm.
Now, if the input goes to 0, the output is not going to blow up. So it's on the verge between stability and instability. It's critically stable. So that's what we are doing here with a little bit of abuse of theory so that we can get some results that are meaningful. That's why I'm giving you guidelines on how to do it. So here, okay, I'm telling you, do it like this, because I don't want you to spend infinite time trying to figure out, so how on earth do I do it? Pick this structure and just go ahead.
Okay.
That's the idea. There are other things I would like you to do. This, by the way, is from a very real process with a company where I had a student who interned, and they had this very problem. Interestingly enough, the engineers figured it out heuristically after a long period of thinking how to redo the whole thing.
It sure seems like just doing a feed forward controller based on the FM would be the easiest thing, but that's not part of the problem.
It's not simple because if you only do feed forward, you mess up the downstream part. So it needs some thinking. And like I said, there are engineers who thought long and hard about it, figured it out heuristically. They did a very good job. So my student's internship was, can you figure this out using some basic theory? So you can, but it's not simple. It's easier if you think heuristically, actually. But it's interesting also to see that the theory does apply as well.
One more question about this problem. Would you expect that if you tried to use the ultimate gain method, would that work?
I don't know.
Yeah, I tried, and it was very difficult to get it into an actual kind of stable sinusoid.
Yeah, the interesting part here is that it's not in the controller design, I mean, the control law part where things become interesting. It's in the control structure. Essentially, you take the average height and you create a loop for that. It's a feedback loop for the average height. If you look at the very end where this goes, we published a paper on that. Well, I didn't cite it here because I didn't want students to just look at the paper and copy everything from here. One student figured it out actually, so but they didn't copy things correctly. But nonetheless, I'm going step by step as you see, and I'm guiding you as to exactly what I would like you to think about. Simple things, not very complicated. I can send you a copy of the paper so you can see all this is a simple part of the paper, and there is more in the paper actually that shows you that the theory can guide you to determining what the engineers figured out heuristically, which is, let me take the average height and use that as my control variable. Go figure, why on earth is the average a good idea? Well, it's because it has more mass and that's a slower system, and it doesn't let any of the three tanks oscillate violently. So what the heck, it should work, and it does work.
Interesting.
The theory corroborates that indeed.
Okay, thank you.
Yeah. Any other questions? Yes. This is from the room. If you cannot hear it well, I'll repeat it. Example 6 in the notes. What note? Which notes? Discrete time system notes. So I think I had this open. No, so let me find it. So example 6 is right after this. Okay. You just follow the formula from the previous page. From the previous page, it tells you how you find phi. Okay. So you just have this pi, you write it in the form rho times e to the j phi. That's a complex number. If you don't remember that, not to worry, I have an appendix in the notes. No, pi is this number here, which is the pole. In example 6, it has the pole, which is root. I mean, the poles are 1 and 0.2. You just write this, you just do everything and it comes out okay. Let's carry this offline. It's direct application of this. Okay. Of the formula. So you have P and P bar. This is P, and this is P bar, right? 0.91, 0.42. So the angle whose tangent is this is fine. Any other questions? Okay, hearing none, I'll stop here. You know how to reach me. I'll try to make sure that I keep Slack open in case there are more questions. We'll stop here and I'll try to finish the problem statements by tomorrow evening so you can start, have the whole Friday to work on this. And the weekend, of course, and Monday. Okay?
Yeah, Friday.
Yeah. Thank you all.